Good morning to all dignitaries. I am Dr. Satyabrata Behera from Indian Institute of Technology, Kharagpur, India. I am here to present our research paper, a mathematical model for estimating near-field peak particle velocity in a 3D space surrounding a blast hole. We are happy to be a part of FRAGBLAST 13. We would like to thank the organizer and all the sponsors to provide us with an opportunity to present our paper. Now, let's understand what is this 3D near field vibration model, why is it required, and its importance. The model is developed for optimizing the negative outcome of blasting, that is the backbreak. As we know, the raw material demand of our world is increasing day by day. We can take the example of coal production demand of our countries. So, what is happening? Day by day, the production target of every mining industry is increasing. To fulfill the target, industries are practicing large-scale blasting operations because blasting is one of the popular technique to break the rock mass. Why it is popular? As it can be applicable to all type of geoterrain and its economic viability. However, it is found that only 7 to 25% of energy is actually utilized in the rock breaking process, and the rest energy is wasted in the form of blast-induced vibration, air over pressure, noise, heat, light, fly rock, etc. Further, breaking of rock mass can be divided into two types. One is desirable rock breaking zone and the other one is undesirable rock breaking zone. Improper utilization of explosive energy leads to undesirable rock breaking zone. That means breaking of rock mass beyond the desired zone, and it is called the blast-induced rock mass damage. In surface blasting, blast-induced rock mass damage zone is called backbreak. Here in this diagram, these circles are the blast holes and this dotted line is the desired damage envelope. However, after the blast, it is found that some extra amount of rock mass has been damaged, and that is shown by the red line, which is beyond the desired damage envelope. That zone is called backbreak. Why this backbreak is so important? Now let's see some negative impacts of backbreak. Backbreak leads to safety issues in open cast mining operations. Sometimes, due to high amount of backbreak, the entire bench got damaged, leading to a high wall condition. It creates problem in the further mining operation. Second one, damage to machineries, loss of productive time. Backbreak form loose hanging boulder in the mine face, which needs to be handled with the help of an excavator. Handling such faces by excavator damages bucket teeth. Sometimes rolling boulder damages to the shovel also. Conducting a second blast round in a backbreak zone without dressing the face increases the chances of fly rock. All these situations lead to a higher maintenance and lower productivity in the mining operation. Therefore, knowledge of the extent of blast-induced rock damage may facilitate the mines to become more safe, productive, and well managed. Therefore, it is required to establish a model which can predict the rock breakage zone before the blast, and accordingly the blast design can be adjusted for restricting the breakage zone within the desired line of excavation. There are various theories applied by scientists in the estimation and prediction of blast-induced rock mass damages. Some of the established theories are vibration-based models, geophysical estimation models, soft computing methods, empirical models, finite element methods, etc. Among these, the popular one is vibration-based models. In the vibration-based models, blast-induced ground vibrations are measured in ppv, that is peak particle velocity. Then, threshold limit of ppv is determined, which is the minimum level of ppv at which the rock is damaged. Taking the threshold limit of ppv For rock damage, various researchers have predicted the extent of blast-induced damage zones. Some of the vibration-based models are mentioned here. In this study, one new 3D near-field vibration-based model is proposed to estimate the vibration at any near-field point in the 3D space, which is difficult to establish in the earlier models. This model is the modified version of Holmberg-Pearson 1979 model. This is the schematic view of vibration modeling in the 3D space. In this model, the Blasthole is positioned along the z-axis. O is the bottom of the Blasthole. P is the point for which we are going to measure the near field PPV. H is the height of the charge length in this Blasthole. Then, to cater the effect of charge length in determining the PPV, the charge length is divided into finite element length, that is del T. Then in this model, the model assumes that elemental waves from each segmental charge are reaching to the point of measurement simultaneously, and thus the resultant PPV can be obtained through summing up all the PPVs due to each elemental charges. Then, in general, the vibration is measured in three orthogonal directions, that is longitudinal, transverse and vertical, and the resultant amplitude becomes the peak vector sum of the same. So without taking the algebraic sum in this model, the vector sum is considered. So now the angles are assigned between the resultant PPV from the each segmental charge length with the longitudinal, transverse and vertical directions. Then the PPV along the longitudinal direction will be Vx, along the transverse direction will be Vy, and along the vertical direction will be Vz. And then the resultant PPV will be Vr. This equation 4 is a 3D near-field vibration model developed by Behera and 2021 for the estimation of blast-induced damage zone. The effectiveness of the model is tested by conducting two case studies, one in sandstone rock mass and the other one in the limestone rock mass. 3 blastomes were designed and executed in the overburdened rock strata of a coal mine, which is sandstone. These were designed as per crater blasts, having no free face except at the surface for studying the extent of damage zone from the surface. This is the schematic diagram of the single hole experimental blast. This is the field view, and these are the details. Blastome 1, Blastome 2 and Blastome 3. These 3 blastomes, the Blasthole length is 1 meter. The charge content in the Blastome 1 is 700 gram. In the Blastome 2 it is 500 gram, and in the Blastome 3 it is 300 grams. K, alpha, beta are the site-specific input parameters for the model, which were determined by conducting regression analysis between the measured PPV and the scale distance. After the blast, the extent of visible crater distance observed in case of Blastome 1 was 70 cm radially from the charge column. And then by utilizing the 3D near-field vibration model, which is given in the equation 4, the PPV level at 70 cm is determined, which is 335 mm per second. This PPV level is considered as the threshold level of PPV for rock damage for this site-specific rock mass. Then, by considering the threshold level of PPV 335 mm per second, the damage envelopes were generated by utilizing the 3D near-field vibration model. These are the damage envelopes of Blastome 1, 2 and 3. These are the field observations, and they are the 3D near-field vibration model outcome. It is observed that the model is predicting the damage zone in a close proximity of the observed damage envelope, that is a field damage envelope, with a deviation of less than 12%. Now, let's see the case study 2. Case study 2 is conducted in the limestone rock mass to check the applicability of the model in the normal production blastomes. Here also, one experimental blast is conducted to determine the threshold level of PPV for this rock mass, and that is found to be 2044 mm per second. Then, to test the model's applicability To estimate backbreak on regular production blasting, 10 production blast rounds were executed. This is the mine's generalized production blast pattern. Blasting was carried out using nonel in down the hole as well as surface connection. Down the hole delay is kept 200 milliseconds and on the surface 25 milliseconds is connected on the trunk line and 67 milliseconds is connected between the rows. This is a blast pattern of blast round 5. It can be observed that due to delay, no two blast holes are blasted simultaneously. Therefore, for the backbreak calculation in the 3D near-field vibration model, the effect of single blast hole was considered. This is the blast round 5 field observation and this is the 3D near-field vibration model outcome. It can be observed that the field observation of backbreak is 6 to 7 meter and the model outcome is 7 meter. And the rest 9 blast rounds are given in this table. It can be observed that in regular production blast rounds, the vibration model is predicting the backbreak with a deviation of less than 30%. Now let's see the conclusion. Blasting technique is a versatile rock excavation process, however, associated with some unwanted results. In surface bench blasting, such unwanted breakage is called backbreak. Backbreak may lead to problem of bench instability, wastage of explosive while charging for the next rounds, situation of hanging boulder, fly rock, etc. Thus, researchers tried to predict the unintended rock breakages generated due to blasting and found PPB to be an accepted and popular criteria for the prediction of rock damage. Most of the near-field vibration-based predictions are one-dimensional. Thus, one 3D near-field vibration-based model was developed to estimate the PPV near to a single charge column in any direction in a 3D space by utilizing the linear charge concentration Q and site-specific parameters K, alpha and beta. It is found that the model is delineating the damage zone in close proximity of the observed visual damage zones both in the case of experimental blast rounds and regular production blast rounds. Thus, using the 3D near-field vibration-based model, the last line of the blast holes can be drilled to control the damage within the desired periphery line and to improve mine's productivity. These are the references. Thank you.